So, yeah, I was looking at Richard was bringing up Boscovich. Remember that stuff that he was looking at?
Yes.
And then there's this guy, and it's solitrons, and I think Ito would be interested in this, but it's like alternate model.
Is he off to Italy?
Italy, yeah. Right. And then Richard, I got an email from Richard this morning. He's coming in on Tuesday here, so he's staying like 3 days. So.
Welcome to the October 7th edition of the Electric View. I'm Neil Thompson. Today we have Dave, Jim, Heather, Buddy, Robert Sr, and Eugene. We are discussing electric gravity and stellar motions, planetary composition and hollow planets, and how the solar system came to be how it is. Please like and subscribe. Oh, we have Robert Sr. here.
Robert Sr.'s been sitting here.
There, see?
Oh, good. Okay.
I had
Robert.
This time I learned that. But I'll tell you, I just wanted to ask about that thing that you had up on there while you were talking about other things. And this is that plasmons.
Yeah,
the electromagnetic field within electromagnetic plasma.
Right.
And they were very strong, he says. And
yeah. It's an interesting article.
What I was interested in there about what it says is that he wanted to make a bottle that would contain enough energy to hold in fusma or low I guess that's low thermofusion,
right?
Which would also be, that's what I thought the Great Pyramid was, that they use muons, which have a short lifetime. I don't know how they work that, but I thought that that's what they would need to contain fusion, because they had nothing to contain it. If it did, what would you keep it in? Your garbage can lid would blow off. Anyways, I just was reading that, and I don't understand what it was, but if that was what you were going to talk about.
It was just kind of something I ran across that I was scanning with, and I thought it was interesting. Just talking about plasmoids and all our discussion. And here's a model of something based on the Boscovich stuff that Richard was looking at. So.
Yeah. In Figure 4 there on the left side, that's pretty much how our solar system, you could look at that, the local interstellar cloud as being that central figure, and then the actual current filament our solar system is strung on is the part that's wrapped around like that. That's exactly the same thing going on.
So, and the solitons, I've read a little bit about them. It's toroidal idea. This message is coming through pretty loud, as it's been loud, but it's continuing to get louder. It seems like.
I love the fact that Bostick actually got into this. Winston Bostick, and he's like the almost like the middle guy that's forgotten in this whole thing sometimes, because you had Alfvén that came up with the theory, Birkeland that came up with the idea, Alfvén that came up with the theory and put things together. But Bostick was an experimentalist, and he was like, well, look what happens when we shoot two of these guns at each other. Look what happens when we do this. Look at what happens when we do that.
Right.
And so that turned into the idea. And of course he coined the term plasmoids. And that ring that you're seeing there on the screen, and the idea, he's basically, that's how Birkeland currents work. That main string to the left and the other one to the right is one of those loop currents that you would see around, or a ring current that you see around the Earth, and you'd also see it around that stick figure man as a torus that goes up the middle, the two dots on either side. But yeah, it's because you could envision a directional flow going through that ring. And of course, the right-hand rule induces a motion, and that motion becomes a plasma circuit itself. It makes a ring, and we see that in several places. Obviously galaxies and so forth. So it's just very interesting to see that how much the stuff scales.
Right.
And how,
but he's jumping. I mean, he's jumping into redefining what just as Ito's doing, what the electron is and what the proton is with this, as far as this whole spin issue. It's very, very, there's a big rabbit hole around it.
Well, it can't get any deeper. This is the thing. I mean, to come to the conclusion that if it's nothing, if the electron is literally nothing but a response to charge, as Ito has suggested, then why does it even remotely have mass? Like, how is it generating that?
Well, this is the big. That's kind of it's a bit of a fudge that it has. Anyway, the mass is so tiny.
Well, but it's there and it's measurable apparently. Not by. I wouldn't know how you'd measure it. But,
what's your read on that, Jim? On the mass of an electron?
Yes, you smart people.
I'm not sure. I'm trying to look into again exactly why that has the value it does.
Because compared to the proton, right? It's the orders of magnitude difference.
Yeah. Well, that seems to imply an internal. It seems to imply an internal structure to the proton that doesn't exist with the electron. So,
Right. Anyway, really interesting. It's always, just continuing to learn. But I like Arthur Compton.
Yeah. What was his?
Straight out of Compton.
Straight out of Compton. What did? My brain is just now having a basketball court with bouncy cars going through it, and then people rapping hardcore about plasma, and electrons. Yo, bitch, you don't understand what a proton is?
It's really interesting because this is where it's just the hard formality of this, and then you see that it's really not hard at all. So, anyway.
Yeah, there's still that weird quantum thing that happens, even on the solar system scale. Because of the relationships between everything, if you accept that one thing is quantized, even just like we were talking about with Titius Bode, if that's real, then that automatically quantizes everything else, because since orbital periods are a function of the orbital radius, then those have to be quantized, and so on, all the way down the line. Orbital velocities are a function of the orbital radius, so those have to have only the values that, basically quantized.
Yeah, the quantization, but you can also go into when there are harmonic ideas, because the constructive will happen at whole numbers, right? Because that's constructive interference, and then the other ones they would be destructive interference. So you would have rings at those quote unquote quantized. Yeah.
Right. The question I'm wondering about though is, since all these things are related, if you have Kepler's laws, for example, how do you know which one is really the driving? You remember the issue with Titius Bode, even using Don Scott's idea, there's still no reason that we should have that exponential relationship you might expect from the Bessel function, that you would have nice uniform spaced orbits, and we definitely don't have that. And Michael Claridge, his work showed that even in extrasolar planets, there still seems to be that exponential relationship. So that's what you have to explain. But then the question is, which is fundamental? Is it really the orbital radius that's the fundamental thing being quantized, or is it Or is it is it the orbital period, for example, or the orbital velocity, or whatever? I'm thinking we're looking at the wrong term as being the fundamental unit that we should be, fundamental quantity that we should be dealing with. Maybe it's one of the other ones that will make more sense, in other words.
Mm-hmm. Richard Merrick has a really, let me see if I can get this fast, but Richard Merrick has a really tight mapping on it using golden ratio. But let's see. I think it's, yeah, but the accuracy is particularly, it's definitely worth a look at here. Let's see if I can get it up. Let's see. Let's see if I can find the way that he did this. He's mapping it harmonically, obviously, and gets like really tight results. He's using
musical gravitational constant.
He's using that, right? And this is the fractured tritone is the golden ratio relationship. There's a 7.5. The Buddy would probably resonate on a lot of this stuff. But this here's the 7.5. You see this ratio pop up quite a bit in music. So, but once again, just a quick overview of like an idea around it is that you get this natural scaling going in towards the sun, and the 1 over R relationship plays really loudly on it. It's hyperbolic. You get a hyperbolic mapping on it. So without it would get a little bit too deep, and I wouldn't feel comfortable yet to say anything in a formal way. But there's something pointing here that's pretty strong.
So he's basically determining that there's you basically can't predict the orbits of the planets. I wondered. See, this is until we go and see other solar systems. I don't know if we're going to once we have like a dozen of them under our belt in the sense of being able to tell what's really there. Unfortunately, I don't see that happening anytime soon. They're so far away. Even if we could,
if they're there, you can measure the proportions. The proportions are pretty. Anyway, if you see it, it's not like the distance is questionable, but once you have that thing and the things are orbiting around it, those proportions you can get pretty tight. Right?
Well, we noted just from what we've seen so far that our solar system's weird, and all I meant is that most of the exoplanets we have seen are like Jupiter size and orbit close to their parent star. Now, this makes sense in the whole, split. Too much current goes through it and splits it. That's probably how Jupiter came into being. And if this holds true, then Jupiter would have been where Mercury is, and that things got mixed up. And this is the whole Clash of the Titans thing that happened. Apparently, when we look in that Velikovsky Talbot idea of the Saturn thing. But the true sense, though, of all these exoplanets being very large and very close to their parents, or being, binary or trinary star systems, which would, indicate that they are like three stars in a system orbiting each other, getting part of a current. This sort of lends credence to what Jim was saying. Because they were able to split their current, whereas my general hypothesis would say that probably wouldn't be the case, but maybe that's only that way because they're so close together down near the, inside the orbit of Mercury, so to speak, and Jupiter is so far away with Saturn that it's just not splitting well. It's still getting a lot of current going on that way, but and it's these things that I think about because we're just as far as we know, our system is a chaotic mess compared to other ones.
I think that's really interesting, though. But it's interesting that, like, maybe
I'd like to build a ratio there. Go ahead.
Maybe different bodies are receptors, generators. We don't know the word yet, but functionally specific to specific frequency waves, where, like, the sun is sending certain particles, hydrogen, whatever, ions to us, however it's exploding out, and Jupiter is making gamma rays. And we know that Saturn has its types of radiation. So what if it's like a different dispersion of frequency? So one is more cohesive with the production and transferring of gamma rays, and the other one is more cohesive to the production of light waves, and the other one is more into like a radio wave. What if the balance is just dispersed in a different manner?
You're absolutely right. Each ball, we'll call them, each ball is getting a different amount of current, and each one is generating different sounds, radio frequencies, and I just said radio frequencies, but you know, there's gamma rays,
right?
Not, and of course some are glowing, like for example, Venus and Saturn both glow slightly. You can see from the pictures that they have a distinctive, like, little glow about them. Just like we were talking about those clouds the other day, you know, like there's green inside the clouds. You know, it's not water in there; it's glowing. You know, it's like an aurora. You know, and I think you're absolutely right that if suddenly there was just a uptick in current that went through this whole system, then you know, it would change the bands of frequency that the sun is putting out, the bands of frequency Jupiter, Saturn, all the gas giants, especially gas giants. But even us, we have a certain frequency. Like you can tell just without even looking. You can tell by just the radio frequency coming off each planet what planet it is. They are that distinctive. You can never, you know, like once you hear Saturn, you are like, I recognize that's a creepy freaking sound. Jupiter's a whole different ballgame, different sound completely. Saturn sounds like minor tones and it's etheric, you know, like almost like, but Jupiter, no, not the same at all. So it's hard to explain. But you could identify them with that alone, because that's how distinct the sounds are, or the frequencies of radio once translated through a amplifier into sound.
Could we like note this by seeing how the different planets behave when they have different types of incoming waves? Like if there's say like a gamma ray burst coming from outer space toward us and toward our solar system, and Neptune happens to be right in the way, and Neptune reacts when it hits, could that be used as an indicator to measure which planets were receptive to which frequencies?
I would go further than that. I would love to hear them listening to all the planets when they are in different positions. We haven't really started doing this. Like here, 28 years later, we can go. That's how long it takes Saturn to go all the way around. So we go and check in 13, or 13 or 14 years when it's on the other side, what it sounds like and where Jupiter is, and does it change frequency? Because we know that when you have like a wire and or a magnet and you move it close to a high gain amplifier, you can hear movement, so you can hear that something's happening there. So what happens when these two charged bodies are at different places within each other and they form a different resonance? Maybe, like
that would be amazing.
That type of thing, but no one's ever done it yet. At least not to my knowledge. We only have a recording, and we think that it's permanent. Like we listen to it and go, "Oh, that's what it sounds like."
No, and of course it's not. And of course they're like interacting with each other. When I envision how the solar system is behaving and like these strings pulling on one another, it's a cross between the gears inside of a clock and a music box. And when they work together, their resonance weave a tapestry of plasma. Very much like the little cards that they put in big looms to say which patterns will become weave of the blanket, of the fabric. Okay, and so when they all are moving and changing together, this tapestry is going to change how it looks. And I also, when I see it, it's also at a greater scale, where every galaxy also has its own particular function. That's why they're individual. And so they're going to be doing different things and behaving and reacting to each other in different ways, and yet still maintaining a sort of balance that will create the tapestry that becomes Laniakea. So how can we by visualizing them in this way, create a graphic of this weaving? Can you guys see what I'm trying to describe here?
Yeah, I do. I was actually just thinking of a proof of concept right at the beginning. If I want to be easy about it, I would start tracking comets that are going to fly by gas giants or pass through their coma. Like pass through the coma of Jupiter, and to see if it changes the frequency of Jupiter as it goes by because of the interaction between the two plasmaspheres, the comet and Jupiter itself, or something.
We already have Rosetta on 67P, which is Jovahelion and perihelion. So that would be. I mean, we have instruments. We already have the ability to collect that data from that particular. And I've like I always ask
I'd
questions
like to hear
how does 67P affect our weather when it's Jovahelion, when it's out there? It's reacting with Jupiter, which is making the sun. Like I said, there are all these strings like pulling on one another and resonating and vibrating, and it's making something. And the comets are like the little threads that go horizontal, you know what I mean? They're like the little dividers that kind of change the loop. It's interesting.
Well, I just don't know if we've ever had an opportunity to have a radio telescope pointed directly at the like we track it with optical when a comet comes in, obviously, but as it passes by Jupiter, for example, I'm just using it as an example, if it came by, if we were listening for it, especially in the area between the two, like not at the comet and not at Jupiter, but where they would intersect, could we hear a reaction, just like you would hear when you bring one electrode near to the Van de Graaff generator and it starts going, it makes little like hissies and sticky. You know. I'm just picturing it. I don't know.
I wonder if we could do that with Sleuth. Is that just a visual?
They have done it already.
Sleuth is a website you can go on and check out a telescope for a period of time, and they will point it wherever you want it, and you can view it through the internet.
Oh my goodness! Cool. Could you imagine we could do that with a radio telescope, and we get the right time and dates and stuff?
Is it just visual, or are there other instruments available through that type of citizen science data collecting?
I actually have the mind right now to go get an old dish and to actually do it myself. Start plotting
it.
Yeah, get a little thing but I don't.
Train. Do it. The
train is selling it. Yeah.
Well, I could deal with some of the parts, because it's just a matter of listening for radio frequencies and making sure you have a wide enough band to listen and then translate that into sound. I can get that part, but it's the aiming in the right place, because as much as I love astronomy, I know how much it takes just to keep track of the moon in the sky or a star. Because you have to plot it from the relative position of Earth and you're spinning. Right. I would have to buy a program to do that. I'm pretty sure that I would have to buy like a device to spin the thing for it, because I wouldn't know how to program that. That'd be a bit much, I think.
There's quite a bit of literature on doing that and how to do it.
Oh, I'm sure there is. It would just be a whole new thing to learn.
Edmund Scientific. My dad bought a reflector telescope for me when I was a kid.
You mean
it had one on. The reflector. No, reflector.
Okay.
It had the reflection at the bottom. It was 5 inch. It was a pretty nice one. But it had on it like the motor to do the tracking. It was tricky.
My father had one.
Hell. It was tricky as hell to use, and we got it to work a couple times, but like over hours to track one thing.
Well, yeah,
it's really it is tricky.
That's where I had the opportunity when I was younger because we got a 10-inch refractor. Well, we call it refractor, but I know it's a reflector.
That's the mirror on the bottom.
The mirror on the bottom, yeah. And it was the moon was the size of a dinner plate in your eye. You could just look at it like it was right in front of your face, and then you get to see the rings of Saturn, the great red spot. And I never thought. I mean, I thought it was. I was blown away that I was seeing that with my own eyes. And it makes you. A kid should be exposed to that because
very lucky.
This whole seeing things on pictures. Yeah. Anything could be a picture nowadays. I mean, but without the grounding to think, I mean, you're going to end up thinking like, oh no, this is all an illusion made up by NASA and the Earth is flat.
Right.
I like the.
Yeah, not totally.
No, not all the time. I didn't mean it that way, but it would be nice for them to be exposed to be able to see like. That right there is the great red spot of Jupiter. You're seeing it with your own friggin' eyes.
Right.
That's right. Like, oh, we know that planet has rings. Why? Take a look. Here it is, being able to see, you can see 4 moons orbiting, Jupiter. You're like, what? Take a look. Here are 4 of the big moons, Because to me, that would just, it blew me away when I was a kid because I just couldn't believe what I was looking at. I mean, I saw that,
Right.
It gives you an appreciation. I talked about that before. There's something about seeing it in real life, like a cloud chamber showing the ionizing effects of radiation as it goes through the clouds, and makes the vapor trails. And that's not a computer generated image. That's literally hard radiation making clouds right in front of your face, and I find things like that to be very revealing because you're playing with the nature of the universe, and we've been sort of adopting a virtual world, because computers can do anything. I can, altered reality, for example, and I'm not saying that we should stop exploring it, but there's something about real reality too.
The thing that it points at really fast that I find really compelling is it's how we perceive. That ends up being you start looking the other direction. It's like instead of looking out, you start looking in. So this is uncharted territory, by the way.
It's once you get down to it, and actually see what we know about any given thing, you realize how flimsy the evidence is.
It really, you really do. Yeah.
I take them at their word. They know the mass of a proton or electron, but I have no idea how they figured it out. But when it comes to planets, I generally have an idea how they figured it out based on dropping balls on Earth equates to us understanding the mass of Jupiter. That makes no sense.
But it's one approach. It's one approach of an infinite number of approaches.
Well,
this is one that comes through to me.
I think there's more of a limited number of approaches on that particular problem, but I understand what you mean.
No. Well, maybe I can. I know it's a leap of a declaration, but I think just the fact that we have these things like with names. Once you name something, it has a certain. There's an essence to the name, right? Like mass. Mass is a good one.
Yeah. Yeah.
And it's like, what is that ultimately? And it ends up being a question that is not fully resolvable.
At the moment,
I think I could easily argue that.
No, I think you're absolutely
right.
But
I think this is true across the board. So with enough time and effort and calories, I think you could put together a pretty compelling thesis that there's an infinite number of ways of looking at it.
Would a rose smell as sweet by any other name?
Would it? Yeah. Would it? Would it? I don't know.
Well, that's a concept thing, guys.
Would it be, we would think of it as a different thing.
A cabbage or a skunk thistle?
Skunk thistle. I like that.
Yeah.
I'll go with that one. Next time I'm gonna buy someone a bouquet of skunk thistles. That's going to be my new favorite thing right there. Yeah. I'm going to write that down, actually. I'm going to put that right in the description.
That's what I got for you.
That's what roses are for me. All right. But what I meant is that by just the extrapolation of me, even though I don't know how they did calculate the mass of a proton, and perhaps maybe Eugene would know more, when it comes to planets, I recognized that they took balls on Earth, dropped them, got the gravitational constant through the formula worked out by Newton, by the experiments worked out by Galileo, and then said, this is universal. This gravity field is universal. G equals blah. Now, taking that as it is and moving it to saying,
there's a lot of assumptions.
Of course. No, you're right. I'm just pointing out the flaw here, not the benefit.
Okay. Yeah.
What I'm saying is that they determined, because of the way that we're going around the sun and how much we're angling, more or less, and I'm not giving fair credence to the actual process here, but once Kepler figured out the orbits and the way that the orbits are and how it actually motions, like the swing of a pendulum, okay, and the speeding up and slowing down that all elliptical orbits have, putting that into the equation, then figuring out using the gravitational constant and the gravitational formula, they figured out the mass of the Earth and the mass of the Sun. And through that, they started figuring out the mass of all the other planets. Now, because back then it didn't matter.
They declared it.
Of course, it declared it. There's no one weighed these things. But now, at the end of the day, though, here we are looking at the Sun through brand new eyes 100 years later, more than 100 years later. And we see the Sun probably has a surface. It looks like it's covered in some sort of molten liquid, at least. Maybe with islands, which is crazy just thinking about it. And then you happen to have these other things that we called gas giants, and we're flying around them. And now they're taking Juno. Now, notice with the magnetic field of Juno, the recorders on Juno and all the stuff on that, they should have been able to tell how thick that atmosphere is. Okay? And I bet you dollars to donuts they know, and they don't want to tell us. And that's why they're... And I don't want to think that, I don't want to be that conspiratorial, but it's something that they hold... This would freak them out if they realized that Jupiter only had an atmosphere, 1,000 miles thick or something. That's not that thick.
I actually think they reported it's like 300 kilometers thick or something like that.
Well, that would mean that Jupiter cannot possibly be as little dense as it says it is. You know what I mean? That throws that equation all into question, because it should be a giant ball of rock, basically, is what or a giant ball of whatever it is, because it's supposed to be a gas giant. It's supposed to be mostly gas, because the mass that we calculate says that it's light. It's lighter than rock. It's lighter than something solid. And that's the same thing. Well, Jupiter is so light, it's supposed to float in water. It doesn't have one specific gravity. So this is where I find this thing, this is where we end up with the whole, is gravity what we think it is? Is mass what we think it is? Is there a problem with our calculation in mass? And does charge seem to affect mass or gravity? And this is where we've talked about this before. This is all I'm saying. I'm trying to give our viewers at home and my friends here who might not know generally how we came to these numbers and why, for example, we think that that comets are dusty snowballs or whatever, dirty snowballs. That thesis, which they appear not to be. They appear to be rock, So it's that type of thing. But go on, Eugene. Challenge me, please.
Yeah, but density of Jupiter is much bigger than density of comets, for example. I mean, Jupiter is like 1.3 grams per centimeter, whereas comets are like 0.4, so it's like, 3 times more the density of Jupiter. The density
certainly.
of Jupiter is bigger than the density of comets.
Right.
But comets are obviously solid, so why can't Jupiter be solid?
Well, I'm not saying that they can't be, but I think that in my opinion, and obviously Wall's opinion, the general principle of the electric universe says that a comet, and this is the electric comet theory, of course, a comet is rock. It's whatever we think it weighs or its mass is, seems to be erroneous to what we're looking at. We seem to look at something that looks like rock and like just as solid as a mountain. And we know that if we threw a mountain into space, and it would have significant mass. This is a heavy object. Well, it seems that the comet is so not dense that they thought that it must be just snow and ice. And this is their principle. This is what their guiding principle is. And we are looking at this and saying, no, this is a friggin' rock, and therefore something is wrong with our calculations. This is what I mean. This is where it starts arriving and poking holes into the universality of the gravitational constant, for example, or something like that. But we don't know the nuances there. Is it charge that affects it? Is it something we don't know affecting it? That type of thing.
Yeah, well, in this case, it should be variable. I think. I mean, if charge was somehow involved. Given the fact that comets have such an elliptic, highly eccentric orbit,
true. Yeah.
One would expect that the mass would change if the charge would change, and the charge should change because of this eccentricity.
As it discharges and recharges as it goes. I think Jim pointed out that there's actually the right-hand rule applies to the orbit of comets as well as they traverse. They sort of go in a moving orbit, I guess. It keeps going around in a circle. It precesses, I guess. Is that correct, Jim? You mentioned that before, if I'm not mistaken.
Well, yeah, pretty much everything in the solar system precesses, but yeah, it's not so much the right-hand rule. It's just it's just because it's all everything that's in that whole large-scale filament will behave the same way too.
Ah, okay. Well, I just meant when I see the comet is going. Yeah, well, but either way, if it's caused by a Birkeland current or the literal right-hand rule, but there seems to be something going on. I guess I have that feeling sometimes when I see a motion, because we see it with the Pioneer anomaly, but where it's not where it should be because it's being pulled by an electric attraction, so to speak. But I wonder. Go ahead.
Are you not satisfied with their explanation of Pioneer anomaly? That it is because of the heat released by the probe itself, it's kind of slightly accelerates.
No, I'm not really satisfied by that. I'm willing to accept it if it didn't feel like it was reaching, It just feels like they're trying to come up with an explanation within their bailiwick, and they're not considering other options. But you know what? I could be wrong, and I'm willing to accept it too.
It's actually the flyby anomaly more than the Pioneer anomaly that shows where the glitch is, where that that it can't be actual or it can't be orbital velocity that they're measuring. It has to be some other redshift.
I actually have an idea. Maybe it's somehow related to this whole dark matter issue in the way that, if you look how modified Newtonian dynamics tries to solve this big galaxy rotation problem, it basically states that the gravitational law is not strictly 1/r squared, right? It says that it's r to the power of 2 plus some little addition to that, right?
Right.
So
I've seen that theory.
Yeah. So it's modified Newtonian dynamics. So basically, it means that the bigger the distance gets, the more discrepancy between Mond and Newtonian law arises. So maybe just because Pioneer went super far, those large-scale effects, those large-scale discrepancies between, between the reality, so to speak, and Newtonian model have already started to appear, So maybe we're dealing with the same problem that is manifested in galaxy rotation curves here. I mean, in the case of Pioneer anomaly, just because Pioneer went super far, maybe it's already in the area where Newtonian dynamics aren't really applicable anymore.
Well, this is where
at least where we can already detect the discrepancy. That's what I'm saying.
Well, I think that I think that just, but taking from MOND is just one step to EMOND, so to speak, to the Wall-Thornhill proposal of electrically modified Newtonian dynamics, which I think, obviously, just looking at a galaxy, for example, I don't think that the galaxy rotation curve says that there must be more matter. I think that has to do with simply this is the way that electric currents should pinch and a load should be there, and this is the spin that would be caused by it. This is what I'm seeing, so I see that directly. But that's my bailiwick, so to speak. But
yeah, I didn't claim that MOND can explain, or MOND is the preferable way of explaining. I just meant that maybe it's the same kind of problem that we're seeing with Pioneer and galaxy rotation. That's what
I was going to bring it into to say that the MOND idea really plays to this interstellar ideas, because we really have to be careful about this. If we don't understand how if we're starting to shoot objects at other stars through different plasmas, and each time we travel through a plasma, or each voltage shift that this object has is going to possibly affect the mass of the object. Well, we're never going to hit our target because we have the variables are too big. If you're not going to know where it's going to shift to, you can't plot a course. You're going to need to, at least from launch, you need to basically have significant ability to have power on board to shift your direction, to compensate for that, not just a few little gas jets, But I see you're looking at it right now. This is the whole observation and expected from the mass that we should, because of all the light that we see there. This should be the curve, galaxy curve, but we see this curve, and this means that it doesn't follow the rules of Newtonian dynamics. It follows the more or less right-hand rule of electric, but we're not going to deal with that right now. But that's generally what it's following. It seems like it's traveling like it's a solid disk, as Wall would say. But anyway, now just to reach. And I don't think this is a reach, but the alternate evidence, of course, automatically falls to the idea of gravity being changed over time, and we know that, or at least we have some strong indications that this is the case. And I think that one of the reasons that we can do that is because, obviously, dinosaurs, for example, they're just way too big to live. Birds that were too big to fly, that type of thing, megafauna. Seem to indicate either something amazing was happening to the buoyancy of our atmosphere, or that the nature of the world was such that these creatures would not die simply by existing in it. I don't mean to go any further than that, but there's obviously, to be that big, you need a lot of food in this current gravity. You need a lot less if the gravity was less, for example, and we seem to show, in construction, we seem to show larger is older and newer is smaller. I don't know. I don't think that we were suddenly really, really strong in the past. I think that it probably has something to do with the nature of the way that we are somehow gaining mass. The whole planet seems like we on the planet are getting heavier, it seems. I don't know exactly how that's happening. Are we losing charge? Are we bleeding it off through our lightning strikes? As they run across the landscape? Are we slowly winding down to to adjust to our new...
radiating everything out, the entire, I mean, far be it for me to like complain about our mechanistic, materialistic world, but it's like it's all radiative. All the energy.
I recognize that unlike some planets, we seem to be discharging quite a bit. With just the lightning strikes alone and the currents going in the poles, we are not balanced for our electrical orbit. It seems if we were, we would be sort of like a dead ball, nothing going on. But there's some activity now. I'm wondering, has this been, like, it seems that this has been going on for a while, but it also seems to happen in stages. So this is all very hard to wrap your head around, but it's, in my mind, lends credence to the idea that the electrical intensity of a body seems to have a play on its apparent mass, or because if all things being true, everything should be rock. Everything we see is rock. Different types of rocks, but it's rock. And some things we see are metallic asteroids, so we do see those occasionally too, like iron-rich, iron-nickel type of things. But besides those bodies, almost everything else is just rock. Well, if that holds true with our own eyes, we look at a comet, it's rock. We look at the moon, it's rock. We look at most moons, they're rocks. Then should not the sun, on a whole, be made of rock, and so should all the gas giants just be made of rock? Generally speaking, if everything holds true. Well, that's something to consider. This is the type of remaking of a paradigm that we sort of think about sometimes. And I don't know where to go from there, but I leave the floor to you on that, if you guys want to, if you have any ideas.
I actually find it really curious that our planet is the densest in the whole system. And it also has... Yeah, so essentially Earth is insanely massive and dense. I mean, by far, like, again, the most densest planet in the whole system, and also, and somehow also the only planet to have life, at least.
And that idea, by the way, that you mentioned of the densest is the sole reason why we look at the Earth as having a giant ball of iron in the middle of it. And there's almost no other evidence to support that. We know that molten iron can't even sustain a magnetic field, probably. So, this is very interesting stuff to try to, because I've seen Jan Lampert's work there with regards to hollow planet seismology, and the idea that there's a liquid outer core and a point in the middle where we call the inner core that is literally just a hole, would far better explain what we see in the shadow zone when P waves go through the Earth, and so during earthquakes and so forth, and why we see earthquakes down to like 1,500 meters and so forth. I'm not saying that it's 100% true, but that it seems to have a better feel if we just got rid of that whole idea of an iron core in there, because it's only needed to support that idea that we're dense, like as you mentioned, that we're just a dense planet.
Mm-hmm. Yeah, actually, Jan Lamprecht's work is really fascinating. I mean, whether it is correct or not, it's just I find it very, very elegant, essentially. Yeah, well, and I really like it.
That's one of the things I've always liked about the electric universe. Whenever you start exploring, you're looking for simpler answers that are, and you got to be careful not to trick yourself, of course, because, just like I'm trying to, as much as I would love to be declarative, I do not have the formula worked out to say the electrical potential, we'll call it coulombs, of a body affects mass in this way. I have no idea how that relationship works, or even if there is one. However, there certainly appears to be one. But that's all I can say. And I would love to be the person who figured that out. But these are the types of problems going into the nature of gravity and stuff that Faraday was working on till his death. So there's a little bit of hubris to think that you can compete with that man's brain. But we do have the benefit of 100 and some odd years of hindsight, so to speak. So. Yeah, that's some of Jan Lampert's work, Hollow Planet Seismology versus Solid Earth. Yeah.
Okay.
It's
yeah, Jim, you was looking at this, right? You were looking at some of the ramifications of this, right?
Yeah, just that it shows that there's actually it does look like concentric shells where the density does get lower inside. It has to, using the seismic data, and it's because ironically mainstream geologists.
That's the mainstream view right there, by the way.
Yeah, the mainstream.
This is right here. Okay.
Yeah, mainstream. See what they're doing wrong? It's where mainstream geologists don't know their mainstream physics. The idea is that what a physicist will tell you is that sound waves are bent towards the highest density. That's not what the geologists are saying. So what this is mapping is that the density, it has to be greater at the surface than it is down to
the outer core.
In D, it's actually getting lower in density, and then all of a sudden there's a sharp increase in density at E.
That's the conventional view, yes.
What's that?
That's the conventional view, yes. I was just saying the outer core gets more dense, and then the core gets even denser. Apparently, that's what it's supposed to do.
Yeah, but no. What's happening though? Is they're saying that it gets denser as you go down, even in a layer. In D, it gets denser as you go down, and that's why sound is bent up. But that's backwards of the physics.
That seems to be, yes. I like Jan Lambert is the other way around, yeah.
Yeah, what this is actually showing is that the density actually decreases as you go inward, except that then there's another shell, another dense shell, and that's, ironically, you get to the same... That's
the better view right there, that picture that we're looking at, the one with the smaller hole, white hole, right there, yeah. That's because obviously the argument against any sort of hollow Earth, and I'm sorry to interrupt you, Jim, is about it's not nothing livable down there. This is not like Journey to the Center of the Earth stuff. This is looking at it from like how things look like they work. And if you look at also, by the way, this is if you look at geodes are hardest on the outside too. So there's some evidence, and of course, as we know from experiments, about 40% of all electrically carried spheres are hollow, just in the lab. Like if we create them, they have a little hollow point to them. Anyway, go on, Jim.
Yeah, actually, if you actually look at the data, not what the mainstream geologists say the data says, but understand the physics of how sound propagates. And look at the actual data, it's saying that you can get that shadow from a hollow spot too. I mean, it's basically the same picture that Edmund Halley had back in the day. He was showing the Earth as these concentric spheres, like basically shells, hollow shells nested in other shells, and he worked it out. Somehow he said basically from Newton's law of gravity, although I don't see how it is. I suspect all these guys have read even more ancient information. But he had that model. And what I'm telling you is that what the sound waves actually say is that it's at least possible for hollow shells and to match that data, but definitely not this increase in density all the way down. It just doesn't make sense. It's where everybody knew, like all modern day scientists knew in their head to start with, yeah, obviously the Earth is dense at the core. That's what they knew going in, and then they made the data match that. But that's not what the data says.
Well,
the data says that there's hollow inside. There's or at least lower density. I mean, you could explain their observations by having a layer of gas even inside, and it would do the same thing with the shed.
Yeah, there
sound
could
would
be something
propagate.
floating in the middle of that. We would never know. If there was a void, if there's something floating in the middle, we would never know it's there because you can never detect it.
Well, a void would cause a shadowing too, and that if sound propagates through the solid part of the Earth, it's not going to do the same thing when it goes through effectively like an atmosphere to the other solid side. It's what they're saying is there for density is, I am convinced, it's wrong by the basic physics of it. They've got the idea that if you read what the geologists say, they said it's bent towards it's bent in the wrong direction. Then a physicist will say that sound waves are bent by density. It's backwards. So somebody's wrong. Either the mainstream physics says either don't know how sound propagates in a solid, or mainstream geologists don't, but they're telling you a different story. So something's whack right there.
So they could be both wrong, right?
Yeah, that's true too.
Jim, before you go, Eugene, Jim, what you said actually struck me very hard when I realized that what the same problem that we're having here is the same problem that we have with relativity, the hero worship. It's not that we don't have the greatest respect for Newton and his discoveries. It just seems that someone has tacked the word universal and implied never changing to this formula. And it became sort of like the foundation of all astrophysics, and it's such the big crux. It's the X marks the spot. Now they won't mess with that. They consider that sacrosanct, if you know what I mean. It's
tacit. Right.
It is never going to change. It is a foundation of everything. And we're poking at it. And this is because at the end of the day, the reason that there had to be a piece of metal in the middle of the Earth to account for the mass is because the mass said it was this and Newton said it was this. Therefore, Newton's right and there is something there. And that's how they're thinking. And I don't hold to that. I think a much more holistic approach, the way that you're approaching it, just looking at the evidence laid out, makes a much easier. See, look, this picture alone is showing my exact point. This is exactly what I'm looking at here. I see the polarity. I see the fact that there's a possibility of a hole down there, and it would look like it's surrounded by liquid.
Right. I see this the Lysigan rings. I'm not sure about the pronunciation of that, but the relation between that, it's with what Lichtenberg was looking at, and it's this relationship is really, really foundational, I find. And I'm interrupting Eugene. I was going to say, let Eugene go on it. Yeah.
Yeah, I just wanted to say that if you look at the graph, I mean, just from Newtonian approach, if you look at what the gravity inside of let's say solid sphere should look like, it increases with radius. I mean, the lower you go, the smaller the g, the gravity becomes. So, in my opinion, it would make sense if more dense material would actually be on the outside rather than, in the more innermost layers on the inside. That's what I was thinking about. And there's also a curious hypothesis by a Russian scientist, Larin. That's his last name. The hypothesis is called the hydridic Earth. So basically what he was talking about, he was starting from the nebular hypothesis, whether you agree with it or not, but anyway, he started from the solar system nebula hypothesis, and he also took into account the electric potential of the elements, which is, I think, mostly ignored by mainstream, accretion type scenarios, most of the time at least. So he basically states that because of this electric, sort of somehow, I mean, a little bit related to this whole Markland convection kind of thing. He claims that it follows from such an approach that Earth should have a lot of hydrids inside of it. So more, I mean, hydrids are compounds with hydrogen, obviously. So maybe it's not so dense on the inside, and there's lots of hydrogen also. And he claims that this is the reason why we have, well, perhaps earthquakes and so on. So there's sort of outgassing from the inside, you know, when these compounds disintegrate or something like that. And in his opinion, that it might also be a reason why we have organic compounds underground, basically oil and gas and whatever else. And perhaps it also causes volcanic eruptions, which are mostly water, actually. So it's also lots of hydrogen. And in the mantle, we actually know for certain that there's lots of hydrogen and so on, and actually water, although it is supposed that it's in a bound state. So it's like I don't remember exactly what is the name of those minerals, but essentially there's lots of water. And so, yeah. And I don't know. I also wanted to talk about Jupiter a little bit.
Sure.
I think, if I remember correctly, Juno confirmed, well, I've already mentioned this, that the atmosphere is only like maybe 300 kilometers thick. That, of course, depends on, you know, where you put the outer boundary on it. So, I mean, what do you consider the start of an atmosphere, so to speak? Because it's obviously not there's no like strict limit to it. It just falls.
Right.
But anyway, the point is that under these 300 kilometers, Jupiter rotates like a solid body, essentially. So like a rigid solid body. And, well, it is actually what I expected all the way. I thought before, and I think still, that
that's pretty damning.
Jupiter has a solid surface, and even if it's not dense, just if you, divide its mass by its volume, it doesn't mean much. It still can be solid. Again, the case of comets shows us that the solid bodies can have a really small density. And I think that Saturn probably also has a solid surface, although it's even less dense than Jupiter. Saturn is just has a ridiculously low density, but anyway, why couldn't it have solid surface if Jupiter does? Well, at least I think so. And how would you explain the solid rotation if it's not a solid? And I also think that Robitaille is correct when he's saying that Sun is condensed matter, essentially, although it has a density of about the density of water, I think. The average density of the Sun. But if it's, for example, this liquid metallic hydrogen, nobody really knows what kind of density it should have, because we haven't been able to produce it in the laboratory to study it. There have been several occasions when people claimed that they produced this material, but there have been so much criticism about all of them that
I've heard some of them. Yeah,
it's absolutely uncertain at this point whether we actually observed something like that. Yeah.
What's the proportion of the 300 km? What's the diameter or the radius?
I think it's like 60,000 kilometers or something.
Okay.
So if you look at the Great Red Spot, if you can put 3 Earths inside the Great Red Spot. So, yeah, that's yeah. You would never notice it. The atmosphere is thick, but it's not that. I mean, 300 kilometers on something a ball that size is just a very thin sheet.
It's really thin. Yeah.
Yeah, well, the radius of Earth is about 6.5 thousand kilometers, so, and the radius of Jupiter is about 10 times bigger.
Yeah,
so
yeah.
About 65,000, I would guess.
Big boy.
I just keep thinking about sponges, though, because things that are like porous and are less dense than some liquids, like liquid mercury, say, and yet they're still a liquid, right? Because they're not molecularly bound in the same way that the, say, balsa wood is molecularly bound, and yet one is much less dense and has much less weight. So, and I keep thinking about that space age material that looks like it's just like fluff.
Like smoke?
Yeah.
It's an they call it a solid aerosol or something like that? Yeah, I love that stuff.
So we need to maybe think about different types of different states of matter and the density and the way that those things would behave. Because if this is a solid body of some sort, and these are the things that are happening above the surface of it, just slightly above the surface, then they could be indicators of the topography of the land beneath it.
Well, yeah, I could see that. I'm still a kind of the idea of thinking of each of these planets as different and exotic. There's a certain aspect to that which I can appreciate, obviously, because I recognize that they are different. But in the grand scheme of things, they're all made of the same constituent parts. So my feeling is that all of the planets and the sun in this solar system are all made out of rock, and obviously with water pouring into it and other things like that. Don't get me wrong. And obviously it looks like Ito might be right that there is a sort of a change on the sun where something gets to a certain point where it matures and it starts having a lot of iron being made nuclearly. Because that's apparently the point where he said that it becomes very inefficient to make those heavier elements. Beyond that, you need to add power. Not that they wouldn't be created, but they would have to take power for something else. But the rest of the changes from hydrogen to helium and all the way down the line to iron are giving energy as they transform, apparently, in the fusion process. But anyway, I'm not really sure about that. But what I meant is that if the sun is just a solid body that's probably made of rock and iron, and has maybe a liquid iron surface to it, to perhaps maybe something like that, and then the Earth itself has a lot of basaltic rock and granite and stuff, but also has a lot of other types of rock, and this is all sort of fused into a ball, and this is generally what we are. I think that Mercury and Venus and all these other planets are all the same. It doesn't matter their size. That's just a feeling I have. And if that's the case, then something is changing their apparent density that is able to change that. I think that alone, finding that relationship, would be the greatest advance of the 21st century if it holds true. That's just my opinion, because, I mean, that's basically gravity manipulation right there. So.
And what do you guys think about the Jeffrey Walensky's stellar metamorphosis, the thing that you can see on the screen? I mean, the idea is that essentially cool liquids and solids, like planets and stuff, are sort of a remnants of stars that have burnt down and basically, it's just the cooled core of a star or something like that.
I've actually never heard of that. I always looked at this diagram, the Russell-Hertzsprung diagram, as initially as was described by conventional science, luminosity versus temperature or something, and then I like Donald Scott's revision, where it's it's a voltage amperage situation, a surface area to amperage per square meter. Getting that idea, and that seems to be something I kind of get behind that. I'm not seeing. Is it the crux of his argument that they that are just because in a way he's right that they are sort of like the debris of explosions from some of these events where they interacted. I would think that's where a lot of this, a lot of these bodies came from. I mean, Jupiter was born and then from the sun in some cataclysm long, long ago, or whatever, and a bunch of little pieces of debris we call moons and stuff flew out of that and were captured by the system. Some might have become a planet. They were that big. Who knows? Like Mercury, for example. Who knows? But that's just my opinion. But is it the crux of his argument that they are just... I've never heard before.
Well, I just like this idea because it's really elegant, in my opinion. Again, that the stars are sort of super hot objects, but then they can, as they kind of burn their fuel, so to speak, they cool down, and eventually they turn into like liquid cool stuff, and then eventually they turn into like solid cool stuff, sort of, kind of. So the planets in this approach are really remnants of stars or some other type of hot objects, I guess.
Yeah.
So would you say it's going from like a plasma state to a liquid to a solid kind of thing?
Well, sort of like that. Yeah, I mean, in plasma, essentially, what you have is a really disorganized bunch of charged particles. But if you look at liquids and again, gases are already more organized than plasmas in the sense that they're neutral. So the electrons are already bound to the nuclei of atoms. And in liquids, you have even more organization where there is a sort of higher degree of ordering of the atoms. And solids demonstrate even higher degree of ordering where you have several. Well, I mean, the crystal lattice is like super organized matter.
Right.
Basically, when you have thousands of intermolecular distances kind of ordering. So it's just a simple and elegant idea to kind of fit it all together.
I see this as a continuation of when you look at it from Donald Scott's point of view of the surface amperage versus size. That's in my opinion, what would happen if we cranked up the amperage. You could even make planets like the Earth glow, just like a comet glows. But it would have to be a severe change in voltage, because the comet exists so far away from the sun most of the time, and only is near the sun for a very short period of time, which keeps its charge balance significantly different than the sun, which makes it discharge when it gets close to it. But if even without that, I can see this whole trend. I like the idea. I just don't think of it as a burning, because it's not. It wouldn't. These flames are not powered by. The energy here is not powered by the internal burning of these of the fusion, but more of the external processing of electrons, if you know what I mean, as a load.
Yeah, well, in this sense, burning is certainly a metaphor, but it's not so far fetched in the sense that the real burning, the fire, is also plasma. So
yeah,
in this sense,
but I see where he's going. I see where he's going, and I generally agree. But without that, with that careful distinction, I think that there's nothing wrong with that interpretation. And like I said, there's these things were obviously blown apart. I mean, look at Phobos and Deimos alone. We could pretty much trace where they were, came off of, and all this other, and 64 moons of Saturn or something, and of course the thousands and thousands that got captured by the sun and became the asteroid belt, and all the shepherd asteroids before and after Saturn or Jupiter, and of course all the Plutoids out there now, and so there's a lot more going on. I mean, and it looks like there's been some significant activity. Imagine back then, 100 years ago, they had no idea that this was going on. They couldn't imagine. Now it's there's 105 million asteroids out there. That's a lot of debris.
And what do you guys think about Planet 9 thing? There's a massive object somewhere beyond Neptune. Let's see. And by massive, I mean at least of the size of Earth, or maybe even bigger.
I heard that because there was a calculation done based on the orbits of the planets, and that they say that it seems to indicate that there's a high probability of another planet lurking out there with a very large orbit that seems to be affecting the orbits of other planets. That's what I've heard. It was a recent thing, and they narrowed it down to a certain swath of the sky, I guess. They think it should be in here somewhere, but which is a pretty good calculation considering the size of the sky.
Yeah, and I think it's actually a good point. I mean, if you look at this particular picture, you would see that there's certainly something missing. I mean, there's certain asymmetry which is kind of baffling, but at the same time, maybe it's actually an evidence for not the existence of an object which is, on a sort of a stable orbit, but maybe it's an evidence for some events in the past. Maybe this right hand part of the diagram is actually the space from which, for example, the Saturn entered the solar system. So it could have caused all of this stuff on the left-hand side.
Yeah, a planet could easily have been part of that and just went out flying again and due to come back again. And that's and of course these people are also taking their cues from modern astronomy. Because once you, obviously, one of the crazy things is that we love the clockwork idea of the universe so much that we think that we know what the skies were like when the dinosaurs were around, so to speak. And I'm beginning clearly to see that was a bit of a folly. That, we could probably go back down to, 2500 BC or so, maybe a bit before that. I don't know anything beyond that, though.
Yeah, well, so basically what I was saying is that maybe, it's not like a clockwork, so these guys are these smaller bodies are arranged in such a way, not because there is a constant influence from Planet 9 from the right, but because there was an event of their interaction, like a singular event, when, for example, Jupiter or Saturn, or both of them, entered the solar system sometime before, and they perturbed these little guys on the left once, and created this arrangement. But yeah, so I hope you got what I was talking about.
I do. I love it.
Mm-hmm. Oh, okay. Yeah. So maybe they wouldn't find it anytime soon, at least. But actually, yeah. I mean, in general, I would say that probably there are much more objects out there than we know yet. But again, this arrangement I mean, following from the electric universe paradigm and all our mythology and stuff, it might be caused by just a singular catastrophic event in the past, such as the entering of Saturn into the solar system or Jupiter, rather than a constant presence of some other object. That's what
I never thought about that. I mean, I guess I did, but I still just pictured that there could actually have been another part of, like, there's no reason to think that every single mythical object or mythical name is attributed in our sky. Some of them clearly are, because we still track them. But I'm sure that there has been something that has gone through that could have been part of the initial configuration that just kept on going, just like, see ya, bye, But your ideas definitely are worth consideration, because I never thought of it just strictly as, oh no, this is just a result of that particular event, not necessarily indicating a Planet 9 anymore. I can see that.
Yeah, I actually thought about it only now since I started talking about it. Yeah,
that's what this is all about. It's a flow of consciousness. We got to find things that we wouldn't think of normally.
Yeah, sort of, and I enjoy that. Actually, yeah,
good,
thank
nice.
you guys.
Yeah, thank you for joining us. It's really great. What's your feel, Eugene, on Sirius and that relationship between the sun and Sirius and this solar system in general?
Sirius. Well, I find it curious about how the ancients spoke about Sirius as being red.
Yes.
Although you probably heard that story, right? That almost all the ancient sources talk about Sirius as being a red star, but today we observe it as a blue star, and it's kind of baffling. Although it's I think it's a double star, a double system.
Triple.
So there's a huge blue star and sort of a dwarf, maybe red dwarf near it. But maybe, I don't know, I haven't researched it yet, nor actually I do plan to do that. But maybe, the Sirius is I think it's called a wolf star or something like that. So maybe when ancients talk about wolf star, maybe they're referring to Mars, actually, not Sirius. This is the idea that I had. So in this case, the redness would be kind of obviously explainable. But maybe it's actually some sort of electrical, influence that caused Sirius to shine in brighter blue than it was shining in the ancient times. So maybe it was redder, so to speak, like a couple of thousand of years ago than it is shining now. Who knows? In electric universe paradigm, it's totally possible that there has been some rearrangement of Birkeland currents in our immediate vicinity in the recent couple of thousands of years. Especially so if there has been a rearrangement of the solar system itself, maybe it somehow influenced the Birkeland currents that were connected to our sun, and so on and so forth. So this is certainly an interesting case to study, I would say. Yeah.
Right. Jim, what's your sense of it these days after
I still think
the lost star?
Oh, well, I still think that picture of Sirius in the interstellar cloud, that I think when you look at the local interstellar cloud and see where Sirius is, I think, to me, the picture just screams at you what happened and when it turned from red to blue. Again, right there.
Can you elaborate on that a little bit?
Well,
what do you mean?
See where Sirius is. What from I'll just give you all the mainstream data on it. You see the sun's direction of motion there. Sirius is also moving more or less in the same direction relative to those are in through the galaxy. Specifically, Sirius they say has a radial velocity of like 8.6 kilometers per second towards us, which is really nothing if we're moving around 220 kilometers per second around the galaxy. All I'm saying in this picture is you have to keep in mind that Sirius is moving more or less in the same direction we are, and it just got to very recently. This image isn't as good as some of them as far as it doesn't show behind. Yeah, that one. That's good. I'm saying that Sirius was probably red before it got to that. You can see in our history, you can see I'm going to argue you can see a Z-pinch, which Sirius just recently got to. Now, the idea in the history, too, is that our sun was once a red star. It's clearly not a red star anymore. Wall was arguing that. So you would assume that if our star was longer in the past a red star, that maybe Sirius was a red star and recently got to this point. I mean, I see in that image, I see Sirius flowing into that region of where those two clouds kind of spiraled around each other, and that's where it kicked in. I mean, it got its current flow from that. That's a pinch to me. That's the way I see it. But again, as long as you know that, right? As long as you know that Sirius is moving in the same direction, and it had to have come to. Remember, we're flowing relative to those clouds. Those clouds aren't moving with us. So Sirius, it's I'm having trouble explaining it. I just see in that picture. I see our history. I see that like our history, just like in those clouds. If you can understand the dynamic of what's happening there.
Well, I don't exactly know because obviously this is an artist's rendition of them trying to see something where they're trying to envision clouds themselves. Obviously, the other artist's rendition was much more wispy and had a direction.
Yeah, one's trying to get the larger scale detail, the flow of the whole filamentary cloud overall. There's the one
that one right there, the one
this one
in the middle on the top, middle, kind of.
Yeah, that one.
Yeah.
That's kind of the same thing, but a different, just on a side. But you can see how there's more of a flow to it.
Right.
Right. That shows like both clouds are cloud, and there's another filamentary gas cloud that seems to be almost twisting around ours. And I mean, you know what that is. But see what
they're literally sustained like a piece of, like a little burning piece of metal ember in a flame. That's what's going on right here. That's how we're powered. And we're just taking a little bit of energy from that flame. But look how big that flame is. And it's not burning flame, it's just drawn from point A to point B flame, current, plasma, whatever.
See that whole thing, that's all the mainstream articles, that's what I was fascinated with, is that structure. And the mainstream knows that we're skimming along in the cloud. Again, they put us on a gravitational orbit, so they think we're going to keep going in a straight line, the way it is. But I'll argue that, see the way the star Altair is also skimming the cloud.
Yep.
I'm going to argue we're going to be doing the same thing. We're going to just keep skimming along the surface. Now, the mainstream articles on that cloud, they know that these clouds have radio scintillation screens at their surface, and radio scintillation screens are caused by free electrons. So we've got a source of current as we skim along relative to the cloud. They say that the scintillation screens move with the clouds. That's how they know they're part of the cloud. So if you have the electron's motion pinned to the clouds, and we're moving relative to that, there's your source of current right there. But the mainstream will say that our motion just skimming the cloud surface is only a temporary thing. And I'll say, nope, it always does, and we actually spiral through space around these, filamentary clouds. But all the data is there. If you're familiar with how current filaments work in the EU model, you see all the information with these interstellar clouds. Like you see ionization gradients that vary in depth, which means that's Markland convection. The mainstream sees Markland convection on those clouds. They also see a magnetic field parallel to the surface. What you need in that Bessel function model, there's no radial electric fields in a current filament if it's a minimum energy filament. In other words, if you're sitting on the surface, the magnetic field better be either axial along the surface or azimuthal, but not radial. That also matches with what the mainstream says. In other words, they've mapped out everything that we need for that to be a current filament. And I'm going to argue that
No, please don't. You're too self-critical. You should just let it flow, because it's always good. Neil, you're mentioning this artist rendition, but these are densities that are from data, right? I mean, it's not like someone just playing around.
The problem is you don't see them. You can't see them directly. All you can do is look on sight lines to stars. So to the extent that we can look over to Alpha Centauri and get an idea of how much cloud is between us and Alpha Centauri. That's it. And then when we look out towards, Source Sirius, you can see so much on that sight line. But if you look off at all these other angles, all you can see, even that doesn't tell you how much is close to us and how much is far from us. We pretty much just know.
These are densities as angular densities.
On some sight line. So if with enough stars around, you can kind of map it out, but that means it's still. You could see why they might have trouble mapping out exactly.
I mean, how would they get, for instance, okay, here's if you take a sight line this way, you've got a variation in density along that sight line. How would you explain how they are describing that?
Well, there's a lot of it is tricks, but some of them are still based on guesses. Like if you see radial velocity of the gas, which you can get from Doppler shift, unfortunately that's trusting that all their motions all their redshifts are actually Doppler motion. Like even this, where they say the cloud direction, that's why I'm still suspect on whether they're measuring the actual flow of all these clouds, or if any of that redshift is due to plasma redshift, then we're kind of measuring just different electron densities too, and that's an issue. But so you can only trust the general, the one picture tries to get the general flow of the clouds, and then the other one's trying to capture more of the detail of. But you can see in it that they can be capturing this helical spirals, but they have no reason to believe that the clouds should be helical. But I'm suggesting they're actually catching that, and they actually did a good job of getting that nature in for not having a theory. Clouds should spiral helically. I think they did a pretty good job.
I see it pretty strongly here, but it's maybe my own projection, So.
Right. But that's what I think is even more compelling, is that the mainstream has no reason to believe that that's what's going on. So the fact that they're detecting that at all is a plus. If one of us tried to map it like that, we could be accused of.
It'd be really interesting to find just dive in and dig into the data itself, or who did it or who wrote the papers on it. I'm sure you have, right?
Those papers were always once I had like Don Scott's model of what we should be looking for, and like I said, even before he came along with that Bessel function, I was trying to map out the magnetic field directions in those clouds, and you could see why I had the problem. Like there's no magnetic fields wrapped around it by the right hand rule, and you wouldn't expect that in as Don showed either. I just didn't have that when I first started working on that, and that's what left me puzzled. Like I wasn't seeing what the mainstream sees in those clouds too is magnetic fields that reverse on fairly uniform distance scales. So that's what we should have been expecting from the start. But that whole Bessel function idea is even new as an EU idea. Don didn't even publish that till 2014. So unfortunately for me,
the Boscovich stuff is really interesting.
Yeah,
because the one thing that I see lacking in Donald Scott's model is this variation in the wavelength, which is that's loud to me.
Again, that's the Gaussian part is what caught my eye, because we know that filaments are both their Bessel function and their Gaussian. They're Bessel-Gaussian filaments, and Don Scott focused on the Bessel part.
Right.
But like when you look at how filaments propagate on a small scale, like the optics guys talk about, even how light propagates, it's a Bessel-Gaussian filament. So you don't want to attribute too much to just the Bessel part of it. You got to look at it's the Gaussian part that Boscovich got right, or that's the. I have to look more into that too. I was unaware that you could get that relationship.
Yeah, no, it's a really cool paper. I mean, just as far as scanning it, and then I mean, there's what grist for the mill for sure, grist for Hamlet's mill. But let's see, come down here. Yeah, there's another one here that goes into a little bit more deep on the analytical side. I think really bring it up. But it's interesting he ran across this and then kind of brought it to our attention, and then how he Boscovich is celebrated immensely, in his. I guess it's. Are you familiar with him, Eugene? Much?
Do you mean Boscovich, who the guy from like 19th century? Or?
Yeah.
Well, I haven't really dig into his stuff. I've heard. It's actually funny that I've read about him in Nietzsche's works.
Oh, right.
And Nietzsche, he mentions him as a guy who basically denies the existence of atoms.
Is that, and so Nietzsche had a problem with that?
No, he actually loved it. He said
cool. Okay.
It's a great piece of critique towards the, I don't know how you call it. Well, atomism, basically. Yeah.
Uh-huh.
And I also saw a monument of Boscovich when I was in Milan, Italy. There's a planetarium. I'm not even sure such a word exists in English.
Yeah, no, that's right. That's right.
Okay. So there's a Milano planetarium, and there's a statue of Boscovich there. It's pretty cool.
He's on all the money in. Let's see. I might have it here. I think it might. It's really, really highly celebrated. I guess it's Serbia, I think.
Yeah, his last name certainly sounds Slavic. Maybe Croatia or something like that.
Uh-huh.
Or Serbia, yeah. I mean, Croatia borders Italy, so it wouldn't, or Slovenia or something like that.
Mm-hmm. Mm-hmm.
Or Ragusa, it's Croatia, yeah.
Right.
So I actually have a couple of comments on what you've been talking about, and Jim and others. So when we're talking about the motions, again, those are called peculiar velocities, I guess.
Right.
Those of the order of like 8 kilometers per second and so on. So there's an orbital velocity around the center of the galaxy, which is 220 or 255 or something like that. And there is also a peculiar velocity of the objects that are near us. So they also orbit the galaxy with almost the same velocity that we have, but they also have a small peculiar velocity with respect to us in the sort of, and it's of the order of maybe 10 kilometers per second.
Right.
And there's a huge problem in determining those velocities, and they usually have a really high error bars, like almost like 100% errors. So it's super unreliable most of the time. I mean, it's like, 10 plus minus 10 kilometers per second, so sort of like that. So it might be 10, it might be 20, it might be 0 or something like that. So the astronomy actually haven't figured out how to map these more or less precisely. And it only goes to show how unfit our geometry, our human perceptions are for this, endless 3-dimensional sea of space. We are really fit to orient ourselves on a basically flat surface,
Right.
We have no idea how to orient ourselves in these really complex environments, such as even the very neighborhood of our solar system. So it's really hard to wrap your head around all of it. And it actually is a good way to segue into my next comment, which is about the very laws, especially electromagnetic laws. It's kind of a philosophical thing that I want to say, but anyway, so I would state that our way of viewing electromagnetism might actually not be comprehensive enough to understand what is happening in space. You see, our Maxwell laws, well, they certainly work for our purposes on Earth, and perhaps they might help us describe, what happens to space probes and stuff. But, I mean, who guarantees that they are comprehensive enough to understand what happens in, like, interstellar plasmas, for example, or, the stuff that happens in galaxies? We have no real experience of interacting with this stuff, and perhaps even our understanding of electromagnetism is not complete.
Right.
Maybe in maybe we miss a lot of stuff. Maybe we don't even have organs of perception, to relate to, in the sense, maybe we can't even detect many of the stuff that happens around us.
Right. I mean, this is a major problem I have with the academia, that it's the opportunity to model and explore, which is right at our, right at our door here. It's a super exciting thing to try to model some of these questions, and the presentation of, it's all, there's these icons that have solved all this, and you're to ask is just immensely audacious, and it's like it shouldn't be, because this is a particularly arrogant position from any 5 sensed being, compared to the possible things that we could sense.
Yeah, and I mean, the very history of development of electromagnetism is basically making the invisible stuff visible.
Right.
We cannot perceive the, for
this
example,
is just one invisible thing, or just one set of invisible things.
Yeah, we don't have an organ of perception of magnetic field, for example. So we have to use external devices such as pieces of iron, like in a compass, for example, to even, see that magnetic field is there.
Right.
And we don't have an organ of perception to see ultraviolet or infrared or radio waves. So we have to invent other stuff that does react to those things.
Right.
So who's to say that there is no other sort of invisible things, invisible yet, that we just cannot detect because we don't have any instruments to do that yet.
Right.
So
we have this imperative for certainty. So it's like, and I think this is part of like how we psychologically get, we buy into it. They know, we know I'm part of this. We know, and that's exciting too. But the certainty level is illusory.
I was reading this commentary on symbolism today. Actually, I was trying to dig out the name of the person who wrote it. But one of the quotes in it was that symbolism is the visual. It is the seeing what can't be seen. It's the visual, turning the invisible into something visible. So when we look at a symbol of something, lots of different things come to mind. We can kind of like tap into a different, a whole realm. It's like a picture's worth 1,000 words kind of a thing. And so the idea is that these things that we're looking at, like you're saying, like we can't see radio waves, but we know they're there. And what we do is we translate things. We find these things that we can't see, and we use utensils that react to them, and we use those reactions as a translation from what they are to what our senses can perceive. So
that's a great point, yeah.
The symbolism that was used, the symbolism that was used from ancient time up until now, everything is insinuating something. It's got a reason for being what it is. You're just like, I'm going to make this one a smiley face, and I'm going to make this one a little heart, and you know what I mean? Like we don't assign symbolisms and wingdings. We actually attribute a very specific function to each aspect of the form, so that when we look at it, we can read what was the intended message, what is the intended function, what is the why is this way, and it makes it more easily read than like a very long explanation or something. Like you can look at do not throw this in the dryer, it'll just say do not iron, and there's like a picture with and I don't have to write all that out, and it's like what can we derive from the symbols assigned to better understand the function.
Mm-hmm.
Mm-hmm. And I actually want to sort of finish my point, I guess. So my general point, no, you weren't interrupting. I was just thinking. So anyway, so my point is that there is no guarantee that our understanding of electromagnetism is complete. And I believe that even the picture of electromagnetism that we have today I would claim that it would certainly evolve to include many more stuff than we can possibly imagine, basically. I would say that there is so much that we miss today because it was developed from super limited set of experience. And as long, so far that we would have more and more experience, our understanding of electromagnetism would be broader and broader. And so maybe I would even claim sort of a heretical point of view here that even the electric universe is not a comprehensive approach. to things. I mean, the universe is even more complicated than just being electrical. It's just our current understanding of what is electricity and magnetism and plasma and whatnot is much more limited than what the universe can offer us, you know. So electromagnetism is sort of a tip of the iceberg that we can perceive based on our experiences from life on Earth, but actually it's much more broader field of experiences. It's just that we didn't have them yet, and perhaps we would experience them someday. I mean, becoming a spacefaring species and so on, maybe going to other planets, maybe we'd have more experience dealing with that stuff. And I'm almost certain that Maxwellian electromagnetism would be someday considered only a really limited and partial knowledge. It's just that we don't have enough experience yet to embrace this broader paradigm, so to speak. Mm-hmm. So electric universe, in my opinion, is just the first step in this direction. But even our understanding of four fundamental interactions is flawed in this case, in this regard, because it's really only what we were able to perceive here on this planet with our sets of instruments and our sets of organs of perceptions. But going to other planets and going to other stars would certainly bring us new experiences and so on and so forth. So this picture would certainly broaden because of that. That's what I think.
Yeah, I like it. I mean, the one thing that I find, like, as far as like intriguing imperatives, is the symmetries that you see. I mean, I think we're just naturally attracted to those, and balances of proportion, and then these coherencies, you know. And I think this is part of our thought and everything, what we do.
Right, but we have to remember that balance does not imply symmetry in any regard.
Mm-hmm.
Like, I mean, symmetrical things are obviously symmetrically balanced, but that doesn't mean that things that aren't symmetry can't be balanced in some way.
Right.
So I think that we need to stop looking for so much symmetry all the time.
Well, there's both sides. There's asymmetry. There's the and then the flow between the two, going from like chaos to order and order.
Well,
to chaos.
crystallographic balance.
Mm-hmm.
Because that looks like chaos, except it's not.
Mm-hmm. But they flow back and forth with each other. They're like poles once again. Mm-hmm. So there's a certain coherency to that. There's a balance to that.
Mm-hmm. I just think of Jackson.
One could argue, just you know, I have my impetuous nature, right? but they go back and they go back and forth. They're swinging. Yeah.
And then what Eugene was, sorry, I just lost my track too, because you were saying something that was really intriguing me, and then I got about balance and about not necessarily being perceived what it is that we might actually, like, what we consider weird senses, like I thought that was going to happen, or things like that, like different types of consciousness, different types of energies that we can perceive, that we just don't understand. It's almost like a kid discovering his hands, like a little baby, and they're like, oh,
right.
There's my hands. That experience that you're talking about when you go somewhere new and suddenly the food tastes different, the air smells different, the world is bigger. But then you realize how similar it is after you hang out there a little while. Is that I don't know? There's so many.
It could be totally confusing when it's new.
when it's new, right? And you just kind of have to look at it. Oh, the Jackson Pollock and like throwing the paint, you know, and the just everything seems like it's everywhere, and yet there's a very fluid balance to it. And because everything's affecting everything else around it, it isn't going to be a mirror image of the thing that was before. It's going to be the product of the thing that was before and all of the effects that are coming to it. Just as that thing will affect the next thing the same way.
I actually think that we have more ways of perceiving the world than we appreciate, I guess.
Well,
it's just that we haven't been able yet to wrap them into a sort of a singular black box, if you like. So we have certainly our perceptions of like taste and sound and so on and so forth, and those are already developed. Those are already sort of black boxes that you put stuff in and you get stuff out. I mean, the input is the signal from the world, and the output is your neural response or consciousness response or whatever. And I believe that we have certain perceptions that haven't yet been packed into those black boxes. So we just kind of, I don't know, we just don't have them operating as they could have been yet. Maybe because of the lack of experience, maybe because it doesn't really affect our way of life yet. Again, just because of our limited area of existence, basically limited to our planet and so on. So maybe when we would habitate other worlds, basically space, asteroids, planets, we would be able to adapt to those conditions and wrap those new perspectives, new experiences into some other types of sensory organs, so to speak. I mean, that sounds a bit esoteric, maybe, and a bit far-fetched, but I believe this is okay. And I actually had an idea that maybe other animals already have other organs of senses that we don't have. For example, well, you know that certainly birds and maybe some mammals have perception of electromagnetism. I mean, the pigeons, the pigeons that they use in post offices, well, at some point in the past, they certainly feel
carrier pigeons.
Magnetic field of Earth, so that they could orient themselves through it. And I think there was an article recently that said that maybe crows can actually see the magnetic field lines, like in their retina, almost like literally, and so on. So we can't even feel these things, but they can, and so on. So maybe actually they can even feel some other stuff that we don't have any idea of, you know. This again, returning to my point that our understanding of electromagnetism and nature in general is incomplete at this point. So I was actually having, recently I wrote an essay about aliens. Basically, what I wanted to do is to explore the limits of human perception, in a way to construct the perfect alien, so to speak. Nice. Which would be like absolutely unlike us, and the goal of this was to actually see what is us, so to speak. So by constructing the absolute opposite, I wanted to find out what what makes a human being, essentially. And I had this idea that I was exploring what is life, what is consciousness and so on, what is culture, what is civilization. And I came to this idea while doing it that maybe actually some animals, maybe some fungi, maybe some plants, maybe they already feel other types of fundamental interactions. I mean, so far, physicists have come to 4 fundamental interactions, which is gravitation, electromagnetism, weak nuclear, and strong nuclear interaction, right? But maybe other types of alive species already have organs of perception or understanding of some other types of those interactions. Maybe we should put, I don't know, bacteria or fungi into our, particle colliders or something and see, maybe they would react to it in some way, or maybe they are already reacting to cosmic ray, nuclear kind of processes, so they can feel some new types of particles being created, and because of that, they inhabit certain places where those reactions are more frequent and do not inhabit some other places, and so on and so forth. So it's just such a, I don't know, broad field of research that is so much ignored most of the time by physicists and chemists and biologists. I don't know, it's just really fascinating to think about all of this stuff. Yeah. That's what I wanted to say.
Definitely. Very cool.
Well, it's like that's super, because I keep thinking about the way that reptiles see in infrared, and how when they show it to us, it's like this, skewed color forms, or you're seeing the heat and things, and then like, are they seeing different, say, like different weather patterns coming at us because they can actually see the temperature variance? Does the sky look different from could they see a huge gamma ray burst happen that we don't have the receptors in our eyes to see? Is there other things that are, other organs, yes, but what is different about their organs that allows them to perceive different types of waves as opposed to ours? And can we learn to see things coming through their eyes?
I actually like the concept of, like a canary in a coal mine in this sense. Yeah. Maybe we can use other beings to help us in, I don't know, perceiving whatever type of interaction there is in the universe. Maybe it's actually I think it's a good plot mechanism, or I don't know, a good point for science fiction. If like space travelers would take on their spaceships a certain type of organism, like, I don't know, a magpie or something, because it can sense something that humans don't, it's just a really funny and interesting thought. Like, canary in a coal mine kind of thing.
Yeah.